Okay, pillar is the pillar here is the wooden beam that stands at the entrance to a traditional Japanese house. Carve it into imagination in the shape of a gigantic candlestick, and your work is done. So, wooden candlestick. It's a pillar. This is gold. If this were not one of the most common characters you would ever have to write, I would apologize for having to give the explanation that follows. Anyway, we want to depict bars of gold. Gold bullion with an umbrella overhead to shade them from the heat, perhaps to hide them as well. The bullion is made by melting down all scepters of the kingdom drop by drop and shaping them into bars. As a primitive, it means not only gold, but any metal at all. So this is primitive as well. So umbrella to shade them. The bars made by melting the, I think this middle stroke is the widest. No, the bottom one. Okay. Melting the king's scepters one by one. Add. Metal before is pig iron. Pig iron. Pig iron refers to iron in the crude form in which it emerges from the smelting furnaces. Of all the various forms metal can take, this one shows us metal before it has been refined. Imagine two paragraphs labeled before and after to show the process. Imagine two photographs labeled before and after to show the process. So pig iron is iron before, is metal before. Okay. Crude was the tree that, this was crude. Okay. Okay. Bowl. 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 Bowl suggests a large and heavy golden bowl into which you are throwing all the books you own to mash them into pulp for some outrageous reason you will have to think up yourself. Mashing. So bowl is a big bowl, golden bowl. I'm mashing up the books. Yeah, into a pulp. Copper. Picture an order of monks serving as chaplains for the police force. Their special habit, made of protective metal, is distinguished by a row of copper buttons, just like the cops they serve. That's a chaplain. Chaplain is the member of clergy attached to a private. Oh, okay. Okay. Habit is picture an order of monks serving as chaplains for the police force. Their special habit, made of protective metal, is distinguished by a row of copper buttons, just like the cops they serve. Okay. So copper is the chaplain. Yeah, the habit of a chaplain that has copper. Chaplain, habit of chaplain that serves cops. Copper. Angling. Angling? What's angling? Angling. What's angling here? Tilting or what? The character we learn for fishing refers to the professional net casting industry, while angling of this character refers to the sport. The odd thing is that your angling rod is a golden ladle, which you are using to scoop goldfish out of a river. What is angling? Angling, the sport or pastime of fishing with a rod and line. Okay. Cool. So angling is scooping with a golden ladle the goldfish. Scooping with a ladle the goldfish from the river. Alright. And next we have needle. In frame 10, we referred ahead to this full character from which the primitive needle on the right derives. Since we already expect the needle to be made out of metal, since we already expect that needles are made of metal, let us picture a set of solid gold darning needles. Darning? To complete the kanji. Darning. What's darning? Skill, activity, mending, hole. Oh, okay. So gold needles, a set of gold needles. Needle is a set of gold darning needles. Okay. Last kanji. Inscription. Take inscription in the sense of the name you ask the jeweler to carve on a gold bracelet or inside a gold ring to identify its owner or communicate some sentimental message. It will help if you can recall the first time you had this done and the feelings you had at the time. So, writing the metal in gold, inside gold, yeah. Its name, yeah, gold name, inscription. Add. Tranquilize. Tranquilize. So, golden truth. Truth. Golden truth. The first lie detector machines of the 20th century worked by wiring pieces of metal into the body to measure the amount of sweat produced when questions were asked. It was discovered that nervousness produced more sweat, indicating subconscious reactions when the truth was getting too close for comfort. Nowadays, people can take drugs that tranquilize them in such a way as to neutralize the effect of the device, which is the other means, which is why other means have had to be developed. Okay, tranquilize metal, and truth. People started taking tranquilizers. Yeah. Let's see that again. The first lie detector of the 20th century worked by wiring pieces of metal to the body to measure the amount of sweat produced when questions were asked. It was discovered that nervousness produced more sweat, indicating subconscious reactions when the truth was getting too close for comfort. Nowadays, people can take drugs that tranquilize them in such a way as to neutralize the effect of the device, which is why other means have had to be developed. Okay. So tranquilize, in order to tranquilize, is is to get rid of the metal detector for the truth. Neutralize the metal detector for the truth. Okay, add. With that, we come to the end of part 1. Before going to part 2, it would be a good idea to return now to the introduction and read it once again. The explanation of the method we are following here and the rationale behind it should make more sense now. By this time, you should be familiar with the use of all three the indexes. If not, take a few minutes to go through them one by one, reading the introduction to each and taking note of how they are arranged. As the number of characters you have learned increases, you will find them useful in navigating your way back to the kanji or primitive elements that need reviewing in their original context. Okay. Let's see. Okay. Let's close this and study the characters that we have just added. Renew this, discard. Let's see. Not this, but this. And the notebook. Kanji keyword rebuild. Yeah, study now. Angling. Angling is the fishing hobby. So scooping scooping fish with a golden ladle from the river. Plug, that's the tree that produces balls. We plug it with an umbrella. Pour. Pour is pouring water from a candlestick. Logic. Well, this is the jewel of a computer. Gold. Umbrella shading bars of gold made by melting down the scepters of the kings in all kingdoms. Needle. Well, that's a set of gold needles, darning needles. Pig iron. Well, it's iron, it's metal. Before. It's crude iron. Before. Copper. Well, that's the metal habit of the monks that serve the cups. Lord. Lord, that's a drop of a king, is a lord. Inscription is writing your name in gold. Hall. Hall is being one whole, being king under your own umbrella. Pillar. Pillar is the wooden candlestick. Wooden candlestick. Tranquilize. Well, it's how to neutralize the metal truth detector. Ball. Ball is a metal ball. Ball. That's not the metal bowl where you mash your books into a pulp. Pour. So let's say pour is pouring water out of a candlestick. Logic. Logic is the jewel of a computer. Angling is scooping fish from out of a river with a ladle. Plug. Scooping fish out of the river with a gold ladle. Yeah. Plug is the using an umbrella to plug the tree that spews tennis balls. Pig iron. Pig iron is the metal, the iron before. Copper is the metal on the habits of the monks that serves cups. Needle is a set of golden needles, darning needles. Lord is a drop of a king. Inscription is writing your name in gold. Tranquilize is what you do to neutralize the metal detector, metal truth detector. Gold is the umbrella shading the bars of gold that were created by melting the scepters of kings. All being a king under your own umbrella. Pillar, that's the wooden candlestick. Bowl, that's the metal bowl where you mash up all your books. Into a bowl. Good. Now let's do the other way around, which is Kanji to cure poor. Inscription. Bowl. Logic. Lord. Pillar. Tranquilize. Angling. Gold. Plug. Needle. Copper. Pig iron. Hole. Tranquilize. Poor. Gold. Bowl. Copper. Angling. Inscription. Pig iron. Plug. Needle. Lord. Pillar. Hole. Logic. And done. That's okay. Now we have how many to review tomorrow? 200. 200 tomorrow to review. Yeah, 229 tomorrow. Cool. Okay, that is the end of part 1 and lesson 12. I think this is the PDF. It is. Okay. So I think this is one of the latest paper by Ian Goodfellow, even though it was submitted a year ago, more than a year ago. But I looked on his Google citations and not many big papers after this one. Okay, in this paper we propose self-attention generative adversarial networks, SAGAN, which allows attention-driven long-range dependency modeling for image generation tasks. Again, attention-driven long-range dependency modeling for generative image generation tasks. Traditional convolution GANs generate high-resolution details as a function of only spatial local points. A lower resolution feature local points in lower resolution feature maps. In Sagan, details can be generated using cues from all feature locations. So this is a bit beginning to look like transformers, where they attend to different parts of the input, not just the local input. In Sagan, details can be generated using cues from all feature locations. Moreover, the discriminator can check that highly detailed features in distant portions of the image are consistent with each other. Furthermore, recent work has shown that generator conditioning affects GAN performance. Leveraging this insight, we apply spectral normalization to the GAN generator and find that this improves training dynamics. The proposed Sagan performs better than prior work. Prior work, I think, is the 2014 paper. Oh no, Brock et al. I think this is the Brock et al. It's the large GAN or big GAN. Yeah, large scale training for highly efficient, high fidelity natural image synthesis. I think this is the big GAN one. Boosting the best published inception score from 36.8 to 52.52, and reducing the Fréchet inception distance from 27.62 to 18.65. Okay, I think in the on the challenging ImageNet dataset. I think on the which paper was it? I think StyleGAN. StyleGAN, ImageNet, style-based generator, yeah. Style-based generator. Or not even style-based generator, it's the which one? It's the analyzing and improving. Yeah. I think FID score is in the single digits now. So FID for this is for Sun. Is there FID for ImageNet? FID for ImageNet. No FIDs for ImageNet. Really? Okay, can. Do they mention FID here for ImageNet? I don't think so. I think all their experimentation is done on Celeb HQ, Celeb AHQ, and FFHQ. Yeah. Again, FFHQ. Is there ImageNet? ImageNet. FFHQ. I don't think there's ImageNet here. ImageNet. Yeah. Yep. Never mind. The performance, do it a different day. This one is. This is attention, self-supervised revision. Okay. Visualization of the attention layer shows that the generator leverages neighborhoods that correspond to object shapes rather than local regions of fixed shape. Okay, introduction. Image synthesis is an important problem in computer vision that has been remarkable. There has been remarkable progress in this direction. Okay, I don't see very well without my glasses, but let's continue. There has been remarkable progress in this direction with the emergence of general adversarial networks. Though many open problems remain, GANs based on deep convolutional networks have been especially successful. However, by extremely examining the generated samples from these models, we can observe that conventional GANs have much more difficulty in modeling some image classes than others when trained on multi-class datasets. For example, while the state-of-the-art ImageNet GAN model by Miyato and Koyama 2018 excels at synthesizing image classes with few structural constraints, ocean, sky, and landscape classes, which are distinguished more by texture than geometry. It fails to capture geometric or structural patterns that occur consistently in some classes. For example, dogs are often drawn with realistic fur texture, but without clearly defined separate feet. One possible explanation for this is that previous models rely heavily on convolution to model the dependency across different image regions. Since convolution operation has local receptive field, long-range dependencies can only be processed after passing through several convolution layers. This could prevent learning about long-term dependency for a variety of reasons. A small model may not be able to represent them. Optimization algorithms may have trouble discovering parameter values that carefully coordinate multiple layers to capture these dependencies, and these parameterizations may A small model may not be able to represent them. Optimization algorithms may have trouble discovering parameter values that carefully coordinate multiple layers to capture these dependencies, and these parameterizations may be statistically brittle and prone to failure when applied to previously unseen inputs. Increasing the size of the convolution kernels can increase the representational capacity of the network, but doing so also loses the computational and statistical efficiency obtained by using local convolutional structure. Self-attention, on the other hand, exhibits a better balance between the ability to model long-range dependencies and the computational and statistical efficiency. The self-attention module calculates response at a position as a weighted sum of the features of all positions, where the weights or attention vectors are calculated with only a small computational cost. In this work, we propose self-attention general adversarial networks, which introduce a self-attention mechanism into convolutional GANs. The self-attention module is complementary to convolutions and helps with modeling long-range multi-level dependencies across image regions. Armed with self-attention, the generator can draw images in which fine details at every location are carefully coordinated with fine details in distant portions of the image. Moreover, the discriminator can also more accurately enforce complicated geometric constraints on the global image structure. In addition to self-attention, we also incorporate recent insights in relating network conditioning to GAN performance. The work by Odena et al. 2018 showed that well-conditioned generators tend to perform better. We propose enforcing good conditioning of GAN generators using the spectral normalization technique that has previously been applied only to the discriminator, Miyato et al. 2018. We have conducted extensive experiments on the ImageNet dataset to validate the effectiveness of the proposed self-attention mechanism and stabilization techniques. Sagan significantly outperforms prior work in image synthesis by boosting the best reported inception score from 36.8 to 52.52 and reducing the Fréchet inception distance from 27 to 18.65. Visualization of the attention layers that shows that the generator leverages neighborhoods that correspond to object shapes rather than local regions of fixed shape. Our code is available at Brain Research / Self-Attention GAN. Related work. General adversarial networks. GANs have achieved great success in various image generation tasks, including image-to-image translation, image super resolution, and text-to-image synthesis. Despite this success, training of GAN is known to be unstable and sensitive to the choices of hyperparameters. Several works have been attempted to stabilize GAN training dynamics and improve the sample diversity by designing new network architectures, modifying the learning objectives and dynamics, adding regularization methods, introducing heuristic tricks. Recently, Miyato et al. Proposed limiting the spectral norm of the weight matrices in the discriminator in order to constrain the Lipschitz constant of the discriminator function. Combined with the interesting, I think this is the invertible network, the invertible ResNet paper alluded to Miyato, the work of Miyato, where they said, okay, they do constrain they use spectral norm to but they said they only used a WI, where here they mentioned something about, they mentioned that they used the gram matrix WI transpose instead of WI. Proposed limiting spectral norm of the weight matrices in the discriminator in order to constrain the Lipschitz constants of the discriminator function. Combined with the projection-based discriminator, the spectrally normalized model greatly improves class conditional image generation on ImageNet. Attention models. Recently, attention mechanisms have become an integral part of models that must capture global dependencies. In particular, self-attention, also called intra-attention, calculates the response at a position in a sequence by attending to all positions within the same sequence. Vaswani et al. Demonstrated that machine translation models can achieve state-of-the-art results by solely using self-attention models. Parmar et al. Proposed image transformer model to add self-attention into an autoregressive model for image generation. Wang et al. Formalized self-attention as a non-local operation to model the spatial temporal dependencies in video sequences. In spite of this progress, self-attention has not been explored in the context of GANs. Attention GAN uses attention over word embeddings with an input sequence, but not self-attention over internal model states. Sagan learns to efficiently find global long-range dependencies. I better go back to this. Check out. Within internal representations of images. Okay, Section 3, Self-Attention Generative Adversarial Networks. Most GAN-based models for image generation are built using convolutional layers. Convolution processes the information in a local neighborhood. Thus, using convolution layers alone is computationally inefficient for modeling long-range dependencies in images. In this section, we will adapt the non-local model of Wang et al. To introduce self-attention to the GAN framework, enabling both the generator and discriminator to efficiently model relationships between widely separated spatial regions. We call the proposed method self-attention generative adversarial network because of its self-attention module. See figure 2. So figure 1, we have, Figure 1, the proposed Sagan generates image by leveraging complementary features in distant portions of the image rather than local regions of fixed shape to generate consistent object scenarios. In each row, the first image shows 5 representative query locations with colors dots added. Color coded dots. The other 5 images are attention maps for those query locations with corresponding color coded arrows summarizing the most attended regions. Okay, both eyes. Okay. Figure 2. The proposed self-attention model for Sagan. The X donates matrix multiplication. The softmax operator is performed on each row. Okay, convolution feature maps. So one by one convolutions. These generate the queries. So the number of W's so I'm guessing these, okay. So these the queries, these are the keys. and these are the values. Okay. I'm not sure about the dimensions here. I'm guessing each row here let's see. The image features from the previous hidden layer XCN CN, what is N? Are first transformed into two feature spaces F and G to calculate the attention, where F, so it's a linear, okay. WG, okay. And then a softmax. BJI indicates the extent to which the model attends to the ith location when synthesizing the jth region. Here, C is the number of channels, N is the number of feature locations of features from the previous hidden layer. What does that mean? Number of feature locations of features from the previous hidden layer. The output of the attention layer is O1 to ON, CN, where OJ is V H. What is H? Oh, okay. 1 over N. BJI. Yeah. It's output B. It's output J attending to feature I or value I. Sorry. In the above formulation, WG is RC to C. No, wait. RC complement to C. F is C complement to, okay. Are learned with which are implemented by are the learned weight matrices which are implemented as one by one convolution. Since we did not notice any significant performance decrease when reducing the channel number of C to be C over K, where K is 1, 2, 4, 8 after training epochs. Wait, what? This is too confusing. We choose k equals 8 in all our experiments. Okay. Why is X the image features from the previous hidden layer? X is C times N. How come? What about the width and height? Are these implicit? Like the number of channels. So there's the batch, number of channels, width or height, and width. Are these implicit? Now, are first transformed into two feature spaces. So when you have C times H times W, where is this N popping out from? This is utterly confusing. Is this not the... Could it be that this is not the published version? Again, self-tension. This is the version that I have. But I know it's published in NIPS Europe's. I don't want to go down restrictions, command, okay. Non-local neural networks is what? Wang. I see him. Yeah, outside now. Poster. Generator. Spectral norm. Self-attention. Self-attention is a module that query key value x. Oh, it's flattened. That makes no sense. Why is it done like this? So this transforms it to, yeah, the channels and all locations. Channels, all locations. Does this make sense? I don't know, man. In addition, we further multiply the output of the attention layer by a scale parameter and add back the input feature map. Therefore, the final output is given, yeah. So it's a more like a ResNet, yeah, where gamma is a scalable learner that is initialized to 0. Introducing the learnable gamma allows the network to first rely on the cues in the local neighborhood since this is easier, and then gradually learn to assign more weight to the non-local evidence. The intuition for why we do this is straightforward. We want to learn the easy task first, and then progressively increase the complexity of the task. In Sagan, the proposed attention module has been applied to both generator and discriminator, which are trained in an alternating fashion by minimizing the hinge version of the adversarial loss. Yeah. So this is the hinge version. It's more like the SVM rather than the log likelihood. So this is a bit better because of log and like logarithmics and exponents don't really play well when it comes to gradients. So yeah, this is much better than logs. Yeah. Techniques to stabilize the training of GANs. We also investigate two techniques to stabilize the training of GANs on challenging datasets. First, we use spectral normalization in the generator as well as the discriminator. Second, we confirm that the two timescale update rule is effective, and we advocate using it specifically to address slow learning in regularized discriminators. Okay. Two-time update. Okay, check out. Spectral normalization for both generator and discriminator. Miyato et al. Originally proposed stabilizing the training of GANs by applying spectral normalization to the discriminator network. Doing so constrains the Lipschitz constants of the discriminator by restricting the spectral norm of each layer. Compared to other normalization techniques, spectral normalization does not require extra hyperparameter tuning. Setting the spectral norm of all weights layers to 1 consistently performs well in practice. Moreover, the computational cost is also relatively small. We argue that the generator can also benefit from spectral normalization based on recent evidence that the conditioning of the generator is an important causal factor in GAN's performance. Spectral normalization in the generator can prevent the escalation of parameter magnitudes and avoid unusual gradients. We find empirically that spectral normalization of both generator and discriminator make it possible to use fewer discriminator updates per generator update, thus significantly reducing the computational cost of training. The approach also shows more stable training behavior. Imbalanced linear rate for generator and discriminator updates. In previous work, regularization of discriminator often slows down the GAN's learning process. In practice, methods using regularized discriminators typically require multiple, e.g., 5 discriminator update steps per generator update step during training. Independently, Heusel et al. Have advocated using separate learning rates, 2-time update rule, for generator and discriminator. We propose using TTUR specifically to compensate for the problem of slow learning in a regularized discriminator, making it possible to use fewer discriminator steps per generator step. Using this approach, we are able to produce better results given the same wall clock time. Experiments. We evaluate the proposed methods. We conducted extensive experiments on the LSVRC 2012 ImageNet dataset. First, in section 5.1, we present experiments designed to evaluate the effectiveness of the two proposed techniques for stabilizing GANs training. Next, the proposed self-attention mechanism is investigated in section 5.2. Finally, our SAGAN is computed with state-of-the-art on image generation tasks, modeling the and 5.3 models trained for roughly 2 weeks on 4 GPUs, each using synchronous SGD, as there are well-known difficulties with asynchronous. Evaluation metrics, we choose the inception score and the Frechet inception distance for quantitative evaluation, though alternative exists. They are not widely used. The inception score computes the KL divergence between the conditional class distribution and the marginal class distribution. Higher inception scores indicate better quality. We include the inception score because it is widely used and thus makes it possible to compare our results to previous work. However, it is important to understand that inception score has serious limitations. It is intended primarily to ensure that the model generates samples that can be confidently recognized as belonging to a specific class, and that model generates samples for many classes, and that the model generates samples from many classes, not necessarily to assess realism of details or intra-class diversity. FID is a more principled and comprehensive metric and has been shown to be more consistent with human evaluation in assessing the realism and variation of the generated samples. FID calculates the Wasserstein 2 distance between the generated images and the real images in the feature space of the Inception version 3 network. Besides the FID calculated over the whole data distribution, all 1,000 classes of images. We also compute FID between the generated images and the dataset images within each class, called intra-FID. Lower FID and intra-FID values mean closer distances between synthetic and real data distributions. In all our experiments, 50K samples are randomly generated for each model to compute the inception score, FID, and intra-FID. Network structures and implementation details. The SAGAN models we train are designed to generate 128 by 128 images. By default, spectral normalization is used for layers in both the generator and discriminator, similar to SAGAN uses conditional batch normalization in the generator and projection in the discriminator. For all models, we use Adam optimizer, beta 1 equals 0 and beta 2.9 for training. By default, the learning rate for the discriminator is 4 to 10 minus 4, and learning rate for the generator is 1 10 minus 4. Okay. Evaluating the proposed stabilization techniques. In this section, experiments are conducted to evaluate the effectiveness of the proposed stabilization techniques, i.e., applying spectral normalization to the generator and utilizing the imbalanced learning rates, TTUR. In Figure 3, our models SN on GD and SN on GD plus TTUR are compared with a baseline model which is implemented based on the state-of-the-art image generation method in Miyato. In this baseline model, SN is only utilized in the discriminator. SN spectral normalization. When we train it with one-to-one balanced updates for the discriminator and generator, the training becomes very unstable, as shown in the leftmost subfigure of Figure 3. Training curves for the baseline model and our models with a proposed stabilization technique, SN spectral normalization on G and D, and two times scale learning rates, TTUR. All models trained with one-to-one balanced updates for G and baseline on spectral normalization just on D. FID, nope. Okay. Spectral normalization both on both. Okay, but then it goes up. Okay. Spectral normalization plus TTUR, yeah, makes it very stable. FID goes down. Okay. What is this? Perception score. Okay. Alright, so that's a winner. So spectral normalization plus TTUR. It exhibits mode collapse very early in the training. For example, top left subfigure of Figure 4 illustrates some images randomly generated by the baseline model at the 10K iteration, although Figure 4. Although the original paper, this unstable training behavior is greatly mitigated. Although in the original paper, this unstable training behavior is greatly mitigated by using 5-to-1 imbalanced updates for D and G, the ability to be stably trained with 1-1 balanced update is desirable for improving the conversion speed of the model. Thus, using our proposed techniques means that the model can produce better results given the same wall clock time. Given this, there is no need to search for a suitable update ratio for the generator and discriminator, as shown in the middle subfigure. Okay. Adding spectral normalization both to the generator and discriminator greatly stabilized our model SN even when it was trained with 1-1 balance updates. However, the quality of the sample does not improve monotonically during the training. For example, the image quality as measured by FID and SIS is starting to drop at the 260th iteration. Example, images randomly generated by this model at different So this is without TTUR. Example images randomly generated by this model are when you also apply the imbalanced learning rates to the quality of the images generated by our model SN on GD plus TTUR improves monotonically during the whole training process. as shown in Figure 3 and Figure 4. We do not observe any significant decrease in sample quality or in FID or the inception score during 1 million training iterations. Thus, both quantitative results and qualitative results are demonstrate the effectiveness of the proposed stabilization techniques for GAN training. They also demonstrate that the effect of the two techniques is at least partly additive. In the rest of the experiments, all models use spectral normalization for both generator and discriminator, and the imbalanced learning rates to train the generator and discriminator with one-to-one updates. Self-attention mechanism. To explore the effect of the proposed self-attention mechanism, we built several Sagan models by adding self-attention mechanism to different stages of the generator and the discriminator, as shown in Table 1. The Sagan models with the self-attention mechanism at the middle to high level feature maps. So feed 32, feed 64, achieve better performance. Yeah, so mid-level feature. So it's 128 by 128. So it's the next step. Yeah, achieve better performance models than with self-attention mechanism at low-level feature maps. Feed 8 and 16. Okay, for example, if ID models again feed 8 is improved. Okay, so these are this. Residual. What is residual? The reason is that self-attention receives more evidence and enjoys more freedom to choose conditions with larger feature maps. It is complementary to convolution for large feature maps. However, it plays a small role as the local convolution when modeling. It plays a small role as the local convolution when modeling dependencies for small feature maps. It demonstrates that the attention mechanism gives more power to both generator and discriminator to directly model the long-range dependencies in the feature maps. In addition, the comparison to our Sagan and baseline model without attention, second column of the table, further shows the effectiveness of the proposed self-attention mechanism. Compared with the residual block with the same number of parameters, the self-attention block also achieves better results. For example, the training is not stable when we replace the self-attention block with the residual block in 8, okay, which leads to significant decrease in performance, sure. Even for cases when the training goes smoothly, replacing the self-attention block with the residual block still leads to worse results in terms of FID and inception score. This comparison demonstrates that the performance improvement given by using Sagan is not simply due to increase in the model depth and capacity. To better understand what has been learned during the generation process, we visualize the attention weight of the generator in Sagan for different images. Some sample images with attention are shown in Figure 5 and Figure 1. See the okay. Visualization of attention maps. These images were generated by Sagan. We visualize the attention maps of the last generator layer that used the attention. Since this layer is the closest to the output pixels, and is most straightforward to project into pixel space and interpret each cell. Wait, how many? So n here, n is height times weight. Okay? So the queries become to C tilde times n, and the keys are also C tilde times n. So they become to, when doing the dot product, we end up with n by n. That's correct, n by n, which means each pixel attending to each other pixel. So that's which is, yeah, not too bad actually. Wait. It's not too bad because we already have. Oh, wait. It's 128 to the 4. Yeah, this might be too bad. What is 128 to the 4? Or 64 to the 4. 64 to the 4. What is this? It's 128 to the 3. It's 256. No, wait, not what? No. Sixty-four times 64 times 64. Yeah, that's massive. That is massive. How do they deal with that? What? So this is byte, 16 megabyte. I was looking in the code here. We have here output channel here C tilde, C tilde, right? So we get here is the batch times C tilde times N, which is height times width. Yeah, so this is massive. I don't know how N by N. So it might make sense doing it for 64, but 128, that's suicide. That's suicide, right? Like 128 by 128 by 128 by 128. Right? How much is that? 258 megabyte. No, so these are entries times float 32, right? 32 bits, so it's 8 bytes. Sorry, 4 bytes times the batch size, which is batch size is let's say 64. This is nuts. 68 megabytes. Jesus Christ. 68 gigabytes. I don't think this, like, even if I have one, this is still 1 gigabyte of memory just for one, like, this is just for one image. Does this guy acknowledge the memory? WGAN GP loss, WGAN hinge loss, WGAN hinge loss, not WGAN hinge loss line. Oh, it is the WGAN hinge loss. Oh, in them is the input. Yeah. Where does this guy employ it? Let's see. In forward tension. So out after L3. L3. I'm gonna assume, yeah, I am size. I'm gonna assume it's the like 64, 32, because otherwise it is massive. It is massively massive. Like 64 times, sorry, 64 times 64 times 64 times. This is like 64, 64, 64, 64 times 4. Yeah, you're talking about 67 megabytes. Understandable, but when you have a batch size of, let's say, 64 images, now you're talking about, you can't do it. You absolutely cannot do it. You're talking about 4 gigabytes. This is kilo, mega, yeah, 4 gigabytes. Okay. I don't know. My idea would have been, instead of attending, so my idea would have been, instead for each pixel to attend, um, yeah, so here what this, so here you have X, and so this is X, the input. Here they do one by one convolution, and they get the queries, which is the um, C times N, right? C tilde times N. And there is also the C tilde times N. And there's also, and then they use it with to basically combine with the values, which is yeah. Instead, I would say, okay, out of these, I want to make filters, convolution filters. So out of these, I want to come out and make convolution filters. A set of convolution filters. Okay? And use these convolution filters on the input itself. On the input itself. again on the input itself. And now I have basically heat maps here. And then I dot with this. This is, I think it's called cross convolution. Maybe something worth investigating. I don't know. Let's get back to the paper, finish that paper. I think basically done. It's just to say, yeah, we verified, we made self-attention, and then we verified both spectral normalization and TTR. Okay, sure. I wouldn't really okay. Save is save. Okay, anyhow, I don't want to dwell too long on this. Is anybody even watching? I don't think so. Yeah, no one's watching. Never mind. Okay. Well, that was second. It was a huge disappointment. But then again, I was almost sure it's gonna turn out like this. Anyhow,